Hi and welcome back to another video. We're going to be talking about limits, and we're going to revisit the concept of rates of change as they relate to limits. And so if you haven't yet watched that video that I made, 2.1 rate of change, go ahead and go back and watch that, because we're going to be referring back to some of the things that we talked about in there. But we looked at this video here. I'm going to play it for you real quick.
Oh my God. That's it, we're out of here.
And so we said that as fun as it looks to drop a giant boulder off of a bridge, we made some assumptions there. Assumption number one, we assumed that they were breaking no laws and doing what they were doing. And secondly, I also do not condone you trying this on your own. So most of the time when people do stuff like that, they're either breaking the law and they get in trouble, or they've arranged it ahead of time. So anyway, all of that aside, we talked about how when we drop this rock off of the bridge when it was falling, it fell a distance of 467 feet. We said that it also follows the equation y equals 16t squared, and that will model the position of the rock at any given time, and not necessarily the position, but how many feet it has fallen over a certain period of time. And so we can estimate over an interval the average speed. And so we took a look at a couple different intervals. So we went from time 0 to time 2, and then we closed in and we said from time 1 to time 2, and then we said from time 1.5 to time 2, and we closed that gap down to a quarter of a second. And we saw that our values were approaching a certain number. And then we talked about, well, what if we could get super close? What if we could really shrink down that interval and use the average speed, the average rate of change, which was the slope formula, to estimate the speed of the rock at the instant of 2 seconds. So we kind of looked at that and we came up with a limit formula for that. And so let's kind of review a little bit here. We have our average rate of change formula. So this is our slope formula that we looked at using time and position. And we also discovered, as we close the gap, we get that instantaneous rate. And so that is expressed as a limit. And so if you didn't get these down in your notes, now would be a great time to write this down. So the instantaneous rate of change, which is the speed at an instant, at a time x equals a, is found by taking the limit as h approaches 0. And then this is essentially the slope formula between that time, that instant, and then a slightly later time. We use a plus h. I think in my example we were below 2, we said 1.9 to 2, and really we add h on. And so it's time, you know, in our example in the previous video it was 2 seconds, and then an infinitesimally small amount of time later, and we were finding the slope between those 2 points, and we're saying as the difference between those 2 points approaches 0, as they become the same point, what do we get? And that's our speed. And so this h value is this super duper small quantity, and we have to find it using limits, because otherwise we are unable to evaluate it. So we have to use limits to evaluate the instantaneous rate of change. And so today we're going to apply what we learned in that previous video, which again, if this is like confusing to you, please go back and watch that 2.1 rate of change video. And that will help you get to where you need to be before we can jump into some of these examples. So we're going to extend this to functions that are not necessarily functions about speed or falling objects or distance over time. We're going to extend this information to any function. So the rate of change of a function, which is also the slope of the function. Remember, rate of change and slope, we want them to be kind of synonymous. Think of them as the same thing. So our first example here, we have a function here, x squared minus x on this interval 1 to 3. Question A says find the average rate of change. So average means slope. So this is a closed interval, and we've talked about this in previous videos. The closed interval 1 to 3 basically means we're considering all values between 1, and 3. So this would be another way to write that closed interval notation. This always refers to the x values. So between x equals 1 and x equals 3. So I need to find f of 1 and I need to find f of 3. And I do that just by plugging them in. F of 3 is 9 minus 3, that's 6. So now my slope formula, my average rate, is going to be 6 minus 0 over 3 minus 1. That's 6 over 2. My average rate of change is 3. So that's how we can find the average. Average means use the slope formula between the two endpoints. Now we want the instantaneous rate at t equals 2. So again, we found the slope of this line. By the way, a line connecting 2 points is called a secant. That's called a secant. And now what we want to do is we want to find the instantaneous rate of change at t equals 2. So to find the instantaneous rate of change, I need to apply that definition that we learned, and I need to use that limit notation. So remember, this is the formula that we're using to find the instantaneous rate of change. And notice down here, the slope formula, a is going to go away. So really, when I set this up, really what I'm going to do is I'm going to think about it like this. It's the limit as h approaches 0, and then all the rest of it. So a in this case is going to be 2. So I need to find f of 2. So I go back up to my equation. F of 2, I'm just going to plug it in for x. So f of 2 is going to be 4 minus 2. F of 2 is going to be 2. That's convenient. Now, f of a plus h is f of 2 plus h. So I also want to find that. My biggest tip to you is that as you're getting used to using this notation, plug them in separately and write out what they are. F of 2 plus h means I have to go back up here to my equation, and I have to plug in 2 plus h for each of these x's. And so it helps me to go off to the side and to write it out. And for some of you, this is going to be the way that you need to approach this. So it's 2 plus h squared minus 2 plus h. Now, this looks funky, but this is how it is. And we're going to go nice and slow with this one so that you can get a handle on things. Now, before I go any further, I'm going to have to do some algebra with this 2 plus h expression. So the first thing I'm going to do is I'm going to do my distributive property and multiply it all out. And if you like the acronym FOIL, that's just fine too. So this becomes 4 plus 2, so plus 4h, plus 6, h squared, minus 2, and then anytime I have subtraction, I have to distribute that subtraction through. So it's going to be minus 2 minus h. So I like to do my simplifying first. So I get h squared, let's see, plus 4h minus 1h gives me plus 3h, and then plus 2. Now, it's really important that I get that down. That is my f of 2 plus h. I do that all off to the side. I haven't even put it into my limit notation. So now I'm going to come over here, and I have to include my limit as h approaches 0. Now I'm going to put everything in. So f of 2 plus h is the first part of the numerator. So I'm going to say h squared plus 3h plus 2. Now it says minus. Now I'm going to do f of a. Well, f of a was 2. So this is my f of a, or my f of 2. This is my f of 2 plus h. And it all goes over h. Now I'm going to do some more simplifying. And as I do this, I have to include my limit notation. The only time I'm allowed to drop my limit notation is at the very end when I've substituted in the 0 for the h. Once I replace h with the number that it's approaching, then I can drop my limit notation. If I need to do some algebra, I need to go off to the side of my paper, and I can do the algebra in a workspace, and that's fine. You don't need the limit notation when you're doing the algebra off to the side. But when I come back, anytime I'm writing out the entire full definition of the instantaneous rate of change, I need to include that limit notation. If you drop the limit notation on your AP exam, you're going to lose a point for what we call a linkage error. That states that you are following a pattern, or you're expressing things and you're saying that two things are equal when they are in fact not equal. If you try to tell me that this expression equals a similar expression but no limit notation, it's just not true. So keep that limit notation in. You should only really need to write it 2 or 3 times, especially if you will go off to the side and do your algebra off in a workspace. So as I simplify, I notice the 2's are going to go away. And then I'm going to factor out the h. We did this in the 2.1 video. Again, that would be a good one to rewatch if this is confusing to you. Now, the reason why I have to do it this way is because if I try to put 0 in right now, I'm going to get 0 over 0. And remember, when you get 0 over 0, that's called that indeterminate form. We can't do anything with that. And if you look at what we have going on the right side of the screen here, when I put 0 in and 0 in, I get that indeterminate form. The only way to get yourself out of this indeterminate form is to do some algebra and to simplify. And so what we do is we factor out the h, and that allows us to cancel it away. And we've created that extended function that we've talked about in previous videos. And we end up getting this. The limit as h approaches 0 of h plus 3. Well, that's easy. It's 3. So the instantaneous rate of change is 3, which is kind of fun because if you look at our average rate of change between 1 and 3 was 3, and our instantaneous rate of change is also 3. And what we're also finding here, and what I want to highlight, is that if you think about where 2 is and where 2 plus h is, they're super close to each other. And if I draw the secant between the 2 and the 2 plus h, it becomes a line like this. And it's actually parallel to the pink secant that we drew. And this rainbow, it actually, as h approaches 0, it becomes the tangent. A tangent is a line that is touching a curve in one spot. It is perfectly tangent to the curve, and the instantaneous rate of change is the slope. So that's something we want to hang on to because that's going to come back around. We're going to see that again in the future. But this slope of this tangent line is the same as the rate of change. Remember, slope and rate of change are the same thing. So the average rate of change is the slope of the secant. That's the line that connects 2 endpoints. The instantaneous rate of change is the slope of the tangent. So, fun times. So let's talk about this. The slope of a curve. The slope of a curve, otherwise known as the instantaneous rate of change, is found by evaluating this limit. And this is what we just did. This is no surprise. The tangent line to the curve at point P is the line through P with this slope. So, let's reiterate this. This is the slope of the tangent line. A normal line, here's another little definition. A normal line is the line perpendicular to the tangent. So if we have a curve and we have a point P and we have a tangent line to point P, the normal line, this would be the normal. It would be perpendicular. That's what it means in math to be a normal line. It is perpendicular to that tangent line. Now, let's take a look at what we can do with this. Example 2, find the slope of the curve at y equals 9 minus x squared at x equals 4. And then write the equation of the tangent line. So this is a 2-part problem. The first thing we need to do is evaluate this limit as h approaches 0. And this time my a value is 4. So I'm going to find f of 4 plus h minus f of 4, and it's all over h. Sometimes it's helpful to write it out and put that number in instead of a, and that helps me know what I need to find. Then I'm going to go off to my workspace, and I'm going to find f of 4 plus h by plugging it in for x. So I have 9 minus, and then in parentheses, 4 plus h squared. Now I'm going to do my algebra, and I'm going to evaluate this. I'm going to simplify it. I'm going to multiply this out. 9 minus. Now I have to be careful with this subtraction. This is going to be a little tricky, and this is also the type of problem that a lot of calculus students will mess up on simply because there's some algebra in there and we get so invested in doing the calculus limit part of it that we forget our basic algebra. And let's see if you can see where the mistake is likely to happen. So I'm going to do my distributive property, 16 plus 8h plus h squared. Now notice I have parentheses around what I've just multiplied out. Here's where this mistake is gonna happen on a problem like this. If you're gonna make a mistake, it's probably gonna be here. You need to remember that when you subtract a quantity, you're subtracting that whole quantity, and any subtraction that comes before a quantity needs to be distributed throughout. So I need to do one step, and I need to say 9 minus 16 minus 8h minus h squared. I need to distribute my subtraction through the quantity. And so that brings me to this, f of 4 plus h, 9 minus 16, here we go. So now what I'm going to do is find f of 4. That's the really easy part. 9 minus 16, that's easy. All right, now I'm ready to evaluate my limit. So let's go ahead and plug everything in and see what that looks like. So I'm going to have the limit of f of 4 plus h. Well, that's this expression here, this negative 7 minus 8h minus h squared, minus negative 7, that's the f of 4, all over h. And this is the limit as h approaches 0. Now I'm going to do my algebra, and I'm going to simplify it out. So keep that limit notation. Remember, you only need to write it like 2 or 3 times, depending on how many steps you need to do to simplify. Because we've done a lot of the work up here already before we even plug it into the expression. So here we go. The 7's actually cancel away. Notice that's a theme so far. Negative 8h minus h squared over h. I'm going to factor out the h. And there's going to come a point when you think to yourself, do I really need to write all this? And yeah, most of it you do. You could probably jump to this step. Some of you are going to be in a place where that's very doable to you. And now that I've canceled h, when I plug in 0, I get negative 8 is my limit. And notice when I put 0 in, then I can drop my limit notation. I only had to write it 3 times. It's not that big of a deal. If you do the work up in your workspace, you're going to be just fine. So negative h, and let's actually take a look at the graph real quick, and I'm just going to show you what this would look like. Let's make a connection. So here's the graph of this equation, and here's the point 4, negative 7. That's where we found the slope. And if you look at what I'm about to do, if you think about the direction of this line, and you can kind of see my cursor on the screen, if you can think about the direction of the line, it's going to have a negative slope. And we just said that the slope at this point was negative 8. And does this look like a line that'll have a slope of negative 8? Well, let's take a look. The second part of the problem was to go ahead and to write the equation of the line with that slope. So now what we're going to do is we will write that equation. So it's going to pass through the point at x equals 4. So let's think about what we know about writing equations of lines. Pass through the point 4, and then f of 4 was negative 7. So that's the point that I'm going to use. And then my slope is negative 8. Well, gee, that's easy. I'm going to take this information and use that point slope form. Y minus y1 is my slope, x minus x1. So this is the equation of the line that is tangent. So now let's connect it back, and let's look at the graph and see what it looks like with the line in there. And so here we are back at our graph, and you can see that here is my point P that I have put in there. That's where we are tangent, and this is the equation of the line that we just found, that y plus 7 is negative 8 times x minus 4. So this is the equation of the tangent line. The negative 8 was what we found using the limit notation. The 4 and the negative 7 were the points that we found by plugging in the tangent point into the function. So again, this is making a connection between the thing we're doing analytically on our paper and algebraically and the graphical representation. So here's another one that we can try, and this might be a great example for you to pause the video and try on your own. But if you'd like to continue on with me, you are more than welcome to do that, and we will do this next problem in much the same way that we did the one above. So consider this equation, 3x minus x squared. Find the equation of the tangent line at x equals 1. So my point is going to involve finding f of 1 and f of 1 plus h. So remember, I am going to be evaluating the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. That's my goal. That's going to be the slope of my tangent line. Now, f of 1 is nice and easy. That's going to be 3 minus 1. That's going to be 2. So when I go to write my tangent line, I need two pieces. I need my slope. I'm going to get that from the limit. And I need my point. Well, that's f of 1 equals 2. 1, 2 is my point. So now I need to work to find that slope. So I'm going to plug everything in. And this one, need a little bit more room. Let's change colors so we stand out a little bit. 3 times 1 plus h minus 1 plus h squared. As calculus teachers, we always say, it's not the calculus that's going to get you, it's all the algebra involved. And this is a great example of a problem that has a little bit more algebra intensity to it. So make sure that you follow along and make sure that you understand what's happening with the algebra. So first things first, I'm going to simplify my f of 1 plus h. So 3 plus 3h minus, now I'm going to multiply this guy out, 1 plus h and 1 plus h. And when I do, I'm going to make sure that I put parentheses around that whole entire expression because I'm subtracting. So 1 plus 2h plus h squared. Now I'm going to distribute my subtraction and simplify. And when I combine all my like terms, I end up with 2 plus h minus h squared. So that's the expression that I'm going to be putting into my limit. So let's go ahead and do that now. So the limit as h approaches 0 of 2 plus h minus h squared, and then minus 2 all over h. My 2's cancel again. Oh my goodness. What a pattern I am seeing here. So the limit as h approaches 0, and here's where I'm going to start picking up my algebra, because I know that once those 2's cancel, the next step is always factor out an h. That's just kind of how it's going to be. So we've got h, and then 1 minus h. The h's go away, and then when I plug in 0, my limit ends up being 1. So this is the slope of my tangent line. So now I'm going to write the equation of the tangent line. So my tangent line is going to be y minus y1. Well, that's what I'm going to use. There's all my info. There's my x1 and my y1. So y minus 2 equals 1 times x minus 1. And I'm going to label it tangent, because then the second part says write the equation of the normal line. Well, the normal line is perpendicular. So the only thing that's going to change is your slope is going to become the opposite reciprocal. And the opposite reciprocal of 1 is just negative 1. So y minus 2 equals negative 1, x minus 1. So this is my normal. And just because I am a huge fan of connecting things to graphs, I want to show you what that graph looks like just kind of super quick here. And so here we are. Here's the graph of our curve. Here's the graph of the tangent line at this spot right here at 1, 2. And then this one is our normal line. So remember, it should be perpendicular, and boom, there it is. So it's perpendicular right at that spot, 1, 2. So there we are, a nice little connection to the graph. So now let's take a look at a different kind of an example where I'm still looking for rate of change, and I'm still going to use that limit notation, but this time it's going to be worded a little bit differently. And again, remember, the AP exam is all about asking you to apply skills that you've learned in new and sometimes challenging ways. And so don't be thrown off by the wording of something. Think to yourself, what is it that this question is getting me to do? So this one says the area of a circle is given by this equation. Area is pi r squared. And then it says find the rate of change of the area. Okay, so as soon as I see rate of change, I'm thinking to myself, slope. So find the rate of change of the area of the circle with respect to r. What does that mean? When the radius is 4 inches. Well, I know that rate of change means find the limits. And I know that r is going to be 4. So the limits, remember, the limit as h approaches 0 is f of a plus h. So a is the x value. So if we think of this equation in terms of x and y, we would write it like this, pi x squared. So the radius is really acting like my x. So when I say r is 4, I'm really saying x is 4, the input value, the independent variable. So really what I'm doing is, and instead of saying f of x, I have a function that is the a of r. A for area, and then the x is the input. Well, if r is your input, then our function notation for the area here, we can just rewrite it as a of r. So the letters can change, but really it all means the same thing. To find the area, it's a function of the radius. I put r into the area equation. So really what I'm finding in here is a of 4 plus h minus a of 4, because I'm concerned when the radius is 4. So I need to find these things. I need to find a of 4 plus h and a of 4. Well, a of 4 is nice and easy. I'm going to keep it in terms of pi, 16 pi. And then 4 plus h is just pi times 4 plus h squared. So when I multiply all that out, I get 16 plus 8h plus h squared. Don't forget to write it twice and then distribute it out. There it is, just for posterity. And now I'm ready to evaluate and plug it in. Now my limit, as h approaches 0, I'm going to have pi times 16 plus 8h plus h squared minus 16 pi all over h. Now watch me do this fun trick. We learned some properties of limits, and we said that when we have limits that have a constant in them, like for example, pi, let's make that a little bit better here. Like for example, pi, try to make sure I have the right tool on, highlighting. I can actually factor that out of the entire numerator. And if I can factor it out of the expression, I can factor it out of the limit. So what I'm going to do is I'm going to take that pi and I'm going to factor it out, and I'm going to put it to the outside. Now this is a nice trick because now I don't have to write pi after every term. So I'm going to have pi, and then the limit as h approaches 0, and the 16s are going to go away, and I'm going to factor out an h from the 8h and the h squared, just like I have been. 8 plus h over h. These are going to cancel, and when I substitute 0 in for h, I get 8, and then I'm going to bring back the pi. Boom. There it is. That is the rate of change of the area with respect to the radius when the radius is 4 inches. Now when I say with respect to the radius, I mean as the radius is changing, tell me what the area is doing. So as the radius is increasing by, for every inch that it's increasing, the area is going to be increasing by 8 pi. So as that circle grows, that's what's happening to my area. So let's do one more little example. This question says, at what point is the tangent to the curve horizontal? Well, this is a curious question, so let's think about this. At what point is the tangent, that's the tangent line, horizontal? If the tangent is horizontal, the slope must be 0. If it was vertical, it'd be undefined. If it's horizontal, it's 0. So at what point is this tangent going to be 0? Well, that's essentially saying, at what point is this value equal to 0? Now, okay, let's do this. So f of a plus h is the same as 3 minus 4 times a plus h minus a plus h squared. Ooh, this one's highly algebraic. So let's get working on this. 3 minus 4a, I'm going to distribute that subtraction, minus 4h, minus, I got to multiply this one out, a squared plus 2ah plus h squared. Now I need to distribute my subtraction. This is a crazy high-level problem here with my algebra. Now I'm going to do some more simplifying here. So I'm going to have, let's see, 3 minus 4a. Oh, nothing really combines, huh? But I'm going to rearrange my terms. And I guess that's as good as I get. Now, f of a would just be the equation with an a in it. So 3 minus 4a minus a squared. Oh, that looks familiar. Notice how I rearranged my terms. So now I'm going to plug it into my limit notation. The limit as h approaches 0, f of a plus h is this ginormous thing, 3 minus 4a minus a squared minus 4h minus 2ah minus h squared minus f of a, 3 minus 4a minus a squared. Well, guess what, you guys? All of this is going to go away. I'm going to factor out an h, the limit as h approaches 0 of, let's see, h, and then I'll have negative 4 minus 2a minus h all over h. The h's will cancel as always, and when I plug in 0 for h, I get negative 4 minus 2a. Now, remember, I didn't have a value of a, but a is going to be the point that I'm looking for, because I want to know when, because remember, this is my slope, when is negative 4 minus 2a equal to 0? Well, that's when I have a horizontal tangent. Well, that's easy enough to solve. Negative 2a equals 4. A must be negative 2. So at x equals negative 2, there is a horizontal tangent. Now, just because I like to be thorough and make some connections for you to the graph, let's just take a quick peek at the graph and then we'll be done. So the question was, when will this curve have a tangent line that is horizontal? So in other words, where it touches the graph, the line will be horizontal. And we found that, we solved, and we found a value of negative 2. So here's that spot right here, and you'll notice that, oh goodness, if I were to draw a horizontal line through that point, it would look like this. And sure enough, right then and there, I have a horizontal tangent. And you'll notice that this is a very special spot on this curve. This is a maximum point. And so I want you to think about something as you go on. What kind of places would have horizontal tangents? Would have tangents with slopes of 0? Is it only maximums? Are there any other spots on a graph where you would have a horizontal tangent? So that's my question for you to ponder as you move forward. And just keep in mind that there's a lot of algebra and there's a lot of intense math that you're being asked to do. And for some of you, your algebra skills just might be a little bit rusty, and that's okay. We all make mistakes. I can't tell you how many mistakes I've made because I've lost count. But what I can encourage you with is that you're only going to reduce the number of mistakes by practicing. You will never reach 0, but you can strive to have the limit of your mistakes approach 0. So there you go. Keep at it, you guys. I am here for you. You can do this, and you know, just keep going. You've got this.